Hi guys! Okay, so in this lecture, we are going to first learn about the least squares line, and then we're going to look at what the least squares line equation is. And this is kind of like a crystal ball of statistics. It's like learning how to predict things. Okay, and then we're going to look at dealing with prediction using the least squares line, and then we're going to get into the coefficient of determination. So let's get started. Okay, so in the last lesson, you probably were like, how do we figure out the line? Okay, the trend line. How do we figure it out? And the thing is, in the past lecture, we were actually just eyeballing it. We just kind of drew it in a way that made sense. But there's an actual official rule that tells us where the line actually goes. Okay, and there's so this rule is called the least squares criterion. So it's just one criteria that has to be met that will present where the line has to go. Okay, so where in the world does a line actually go? This is so confusing. But so we're gonna use we're gonna do the old-fashioned way and really calculate precisely where we're supposed to put this line. And we're supposed to use the smallest sum of squares for the whole data set. Okay. So basically, by looking at this, because we'll actually see we'll figure it out as we go. I'll show you how to work through it. But if you look at the picture on the right, the line is already drawn there. But do you see the distance from the dots to the actual line? Okay, the line is supposed to, ideally, the line will be placed in such a way on the graph so that it sort of connects everything, but it has to give the least amount of space from the line to the dots. Okay, and these are the squares. All right, so we want the least squares to that line, whether we're going up or we're going down. Okay, so yeah, I mean, in the future, when you have to draw a line, in your practical life, it really is going to depend on the study that you're doing and how precise everything needs to go, or just how obvious or not obvious your points are on your graph. Because in some instances, you kind of know exactly where the line is going to be. You can really just eyeball it. But sometimes you have to be, precision is key. Okay, and especially in those instances, what do? Well, we use an equation. So I'll show you the actual equation and how you're going to figure out the line in a minute. But first of all, I want to get you guys to remember what happened in algebra, back in high school or whenever you took it. Because we're doing a similar thing. That was almost like just the precursor to what we're going to be doing now. Okay, so remember back in the old days when you're doing algebra and you were given some, points to plot, and then you plotted them right here like that, and they were all in a nice perfect line, and then you just drew your line, right? And then they said, and then we knew that this was the equation for the line, right? Where B was the slope. And remember, the slope was rise over run. Okay, remember that whole thing? And then your A was going to be your y-intercept. This was where, you crossed over the y-axis. So B is always going to be rise over run. That is your slope, right? So to get A back in the old days, we would take one of these points, right? You could take the top one if you felt like it, which was 1, 2. Okay, and you take any of these pairs, right? and you fill in for x and y, and then you back calculate so that you can get your A. Okay. Remember that? Okay, now here's statistics. We definitely don't have a perfect line, obviously, but we can make a line. Okay, yay, statistics, the statistics version. So here's your least squares line in this situation. Pretty much the biggest difference between the equation that you would be using for the old algebra line and the statistics least squares line is the fact that this is an estimate. Okay, so the equation is y with a hat on top right here equals bx plus a, right? Well, this entire thing right here is definitely going to be an estimate because, as you can see, none of these points fall on the line. Oh, so we're just trying to figure out where, what is the least way, the least squares, or like the least distance that we can have from the line to the points, okay? So that is why when you write out the equation, this one's going to have a hat. Okay. Okay, so, I mean, yes, there are softwares, actually Excel, of course, can all do this for you, but it is actually important for us to really understand what's going on with these numbers and how you can get them. And, you know, the reason being, you're probably not going to actually use this in real life, but you might, or you might need to develop something that stems from this. So we do need to learn the manual approach. So the manual approach to calculating your line, actually your y-intercept. Okay, so first of all, you're gonna take all your x, y pairs and you're going to go ahead and plug them into an equation so you can get B. Okay. Then what you need to do is calculate x bar and y bar. And what is x bar and y bar? That's the mean of the x's. Okay, mean of the x's, and then you're going to calculate the mean of the y's. Okay, and that's very important because when you calculate the mean of both, so x bar comma y bar, this pair is actually on the line. Okay, it's on the actual line. Okay, provided that none of the points that we're given in this whole, none of the points that you're gonna get are going to be on the actual line, but the means of your x and y pairs, that will fall on the line somewhere. Okay, so it's very important to calculate this. You figure out your slope, and then we can back calculate it so that we can get our y-intercept. All right, so just so everybody knows that in order for us to even move forward with calculating B, the slope, or anything from this lesson, you need to save your calculations from the previous lesson. That means, remember in the previous lesson, we figured out what R was, and we went through a whole process in calculating R. Remember that? It was really lengthy. We got really annoyed. It sucked. We threw our computer at the wall. It was madness. But we have to save all those calculations because that is going to feed into what we're going to do in this lesson. So we have to build on that, okay, is what I'm trying to say. So everything that you calculated when you calculated R, all of your sums, okay, you're going to need this to calculate for B, or the slope, okay? And also you're going to need it for when we go over coefficient of determination. So do not throw away your R or your calculations. We build on this, okay? Obviously, X bar and Y bar is this is the first time you're doing this. It was not done in R, but you're doing it now. Okay, now we're gonna get into some serious calculations, guys. Okay, so stemming from the problem that we had in our last lesson, okay, we're gonna use that exact same problem because that's where we did all of our work from, right? So remember, just a little refresher, it was about how we wanted to see if there was a correlation between, the diastolic blood pressure of the patients and how many visits that those patients had in the year. Okay, so your X was the diastolic blood pressure reading of the patient. Your Y was the number of appointments that that patient had that year. And then this is just the patient, all right? These are the patients, the individual guys that came in to see this physician. Okay, so these are the formulas that you're going to be using to calculate, well, really to calculate the entire least squares line equation, okay? So what you want to do is look for B first. You have to find B before you can find A because, you need to put B into that equation in order to find A. So what you're going to do is basically recycle all of your information from when you created this chart, okay? And you're going to go ahead and put all of that into your B, your equation, and solve for B. Okay, it should, since we did all the work before, this is just about calculating things, so you should be fine. And then whatever we get for B, you're going to plug in right here, okay, and you're going to solve for A. And remember, Y bar and X bar, these are the means, okay? So you've got a mean for your X's, and then you have a mean for your Y's, and you should have calculated that by now, which of course I'll give you those numbers here. But when you are doing this on your own and working on a different problem, when you come to this point, you definitely want to have your means already calculated. Okay, so the goal of finding your least squares equation, okay, is that you're trying to find your B and your A, okay, so that you can plug it back into this equation. You are always going to have a Y with a hat on it equals whatever your B is, so whatever number, this is going to be a number, okay, times X, so X is always just going to be X, right? It's going to be there, plus whatever you calculated for your A, okay, whatever your y-intercept ends up being, okay. Also, another thing you want to point out is that if A ends up being a negative number, then you're going to have a minus sign right here instead of a plus, okay. Okay, so here we go. Basically all that's over here, this is all, I extracted all of this from that previous lesson, from our previous lesson where we worked on the exact same problem, and we got all this from the table. These were our previous calculations, okay? So I'm not really doing anything new here. I just wanted to put them all on the side so that we have them here and we can go ahead and plug them in where they need to go for our new calculations. Okay, but we have already calculated these things. They're on the previous lesson, and I believe there are a few slides down in this lesson, so you can get those from there. When you are doing a problem like this on your own, of course, like I said, you have to recycle all of your calculations. You're going to need to look back at how you calculated R, and all of these little pieces to calculating R are going to be required to calculate B as well. Okay, so in addition, what I did was I took the means of the X's and the Y's. So how you're going to do that? Well, basically how this works is you take 678, because that's like the sum of all the X's, right? And then you're going to divide it by how many patients there are, there are 7. Okay, so once you go ahead and do that, you will get 96.9. And you're going to do the same thing with the Y. So The sum of the y's was 166, and we're going to divide that by 7 as well, and you should get 23.7. So that's settled. We did that part. Okay. Now, we plug all of the little pieces into the B equation, and we solve for B. Okay, so this is relatively easy, but you do have to pay attention to making sure that the right pieces go where they need to go. Okay, so I went ahead and put all the numbers in their places. So we can just go over this real quick. Look in the equation. Your n is right here. We got n's. Well, our n is 7, so 7, 7. Next, we have the sum of our xy's. What's our sum of our xy's? It's this. So we put that right there. Minus, okay. Then next on the top, we have the sum of our x's in parentheses. Well, that was right here, sum of our x's. And then we have to multiply that by the sum of our y's. Sum of our y's is right here. We want to put that on the numerator. There we go. The numerator is set to go. Now let's focus on the denominator. So like I said, we got our 7's here for your n, and that's supposed to be multiplied by the sum of our x squares. Well, sum of our x squares is right here. So we go ahead and put that right there. Then we're supposed to minus it, okay, by the sum of our x squared. So then we go ahead and find the sum of our x's, and we square that. Notice how these are a little bit different. It's the same concept as last time when I told you guys that these are totally different things. This is squaring the sum of the x's that we have, and this one is square rooting all of the x's and then taking the sum of those. So they're different. They're totally different numbers that we have to put together. Okay. Anyway. Moving on, so now really this is just a matter of order of operations. Okay, let me clean it up a little bit so it's not so messy. This is just a matter of order of operations. Follow the order of operations, you're going to be totally fine. Okay, and how do we do that? We make sure that you go ahead and you're going to multiply this side first, and you multiply this side first, and whatever you get on both sides, then you're going to go ahead and subtract those guys. Okay. So this side subtracted from this side is going to give you 16,658, okay? Then on the denominator, you have to make sure that we go ahead and multiply this side first and then do this side, which is squaring this 678, okay? And then whenever we get on both sides, we're going to go ahead and subtract them, okay? And then that should give you 15,000 or 15.56, okay? No, what the heck? 15. That's a comma. 15,516. Okay, and then go ahead and divide, and our B turns out to be 1.1. Okay, so next step is for us to work on the A now that we have our B, right? So now we work on the A. Here's our A equation. How did we get that A equation? Well, you take it from here. It's like you go, because we have y hat equals bx plus a, right? And you have to get this bx on the other side. So we minus bx from both sides. This is basic algebra. You guys know how to do this. And then you'll get a equals y minus bx, right? So that is how we get that. That's how we solve for a, y minus bx, which is right here. Okay, so now we're just going to plug in the numbers that we have and go ahead and solve for a, and this should be really easy. All right, we already have our x bar, remember? I mean our y bar, sorry, which is 23.7. And then our b we figured out is 1.1, and then our x bar is 96.9. So we go ahead and put everything in their place, and of course you have to pay attention to the order of operations, which means we have to solve this part of the equation first, okay? And whatever this is, we're going to minus it from the 23.7. So after you go ahead and calculate the whole thing, we get negative 80. Okay, negative 80 is our A. So then, now that we have all of our pieces, okay, now that we have all our missing pieces, it is always a good idea to actually check your work. Okay, so how would we do that? Well, we could literally just take our x and our y, okay, our x bar, y bar, and we could plug that into, into this equation. Okay, now that we have our least squares line equation, we can go ahead and plug everything in, and then we can actually see if we get y. Okay, so sorry, we are going to plug in our x using our b and a that we already calculated. Okay, and if we get the y that we already know is, y, then that means that our equation is correct. Our b and our a is correct. So this is what it would look like. You would go y equals 1.1 times, or let's be grown-ups, 96.9, right? Plus, get rid of the negative, plus, minus 80. Okay, so if you can multiply these two and then subtract 80 from it, and you still get 23.7, which is your y, then you definitely did this correctly. Okay, so remember that one rule about the x bar and y bar having to be a point that is on your line, for sure. Okay, so that is the one point that we know will always fall on the least squares line. The other points probably are not going to, okay? But we know that that is there. And now that we know the slope, we can start, we can start plotting and we can draw out the line. Remember rise over run? Well, we know what our B is, so that's the rise over run. We can, the 1.1, so we can, calculate that and go ahead and make a more educated drawing of our line. So the slope, or B, of the least squares line tells us how many units the response variable, or y, is expected to change for each 1 unit of change in the explanatory variable, or x. So I know that sounds kind of complicated with the wording there, but this is pretty much what that means. Pretend we're back on our graph. So for every, increase in x, because this is our x, and then this is our y axis, right? So for every 1 increase in the x, all right, there will be a 1.1 increase in the y. That's what that means. And how did we get that? Well, that was our b, 1.1. So every increase in this, in our x, there will be a 1.1 increase on the y. So how does that play out? Let's see. So we're moving, we're going to start from here, okay, at 1.1 on the y-axis. So let's say when it moves over 1 on the x, so on 1, it's going to literally go up 1.1 more on the x-axis. So it's going to be like, maybe estimated to be around this. Erase. So it might be estimated to be around that much, and then you go up again 1 unit of x, and then when we do that, we'll have to go up 1 unit of y, which is going to be 1.1. So 1.1 could be estimated maybe around here. Okay, so that's pretty much how you would plot your y hat equation. Okay, so that's really what that means. Okay, so now let's talk about some of the influential points. Remember how when we went over R in the previous lesson, we learned that outliers, some of the dramatic outliers can actually cause problems with R and kind of drastically influence the whole equation, right? Like if you had a outlier that was way down here and, it had nothing to do with the rest of the points, it was just a weird outlier that happened, well, you're still counting that in your equation. It's still part of your calculations. And that will dramatically influence how your line is going to be. Okay, so an extremely high x or an extremely low x can kind of screw up your equation or make it look all wonky. Not necessarily wonky, but it'll just look weird because you'll have a line and you'll go, that doesn't look like it was really constructed out of the least squares possible, but it was. You just, you have a weird outlier that is kind of screwing up your equation. So, it's always good, even though you may still have to use your outliers in some situations. If you feel like your outliers can be thrown out, you should check your scattergram for outliers. And, in the future, when you're doing your own studies and you may be using this approach, you might want to throw out some outliers just so it won't screw up your data. Because if you know that those outliers don't really, you're not going to count them, they're not really going to, that they don't really, you don't want them to influence the rest of your work, and you know that it's not going to hurt your data if you get rid of them, do it. All right, so what is the residual? Think of residual as residue or like the leftovers, okay? And really that's kind of what it is. It's like, let me show you on a chart really quick. So we have our x-axis, our y-axis, and pretend we have some scatter plots here, and this is our trend line, our smallest squares line. So the residual is going to be this space between these points and the line. So it's this space, okay? And the whole point is that we don't want to have really big residuals. We want Okay, so remember that I said we were going to finally be able to use like an equation to be able to predict things in the future. Well, this is that part, okay? So what we can do is we can use the least squares line equation. You remember that equation? The h hat equals bx plus a. So the equation that we get, we can use this equation to predict. Okay, so it's pretty cool. What you could do in this situation is use this equation to plug in the diastolic blood pressure, which is your x. Okay, so you can, if you want to predict maybe how many appointments someone might be taking in the future, depending on their diastolic blood pressure, all you would have to do is take your equation and we would plug their diastolic blood pressure reading in for the x, right? And then you would get an a hat out, and that would be your prediction. That would be the prediction of how many appointments that they would take this year, okay? So this is really good for us to use, but sometimes it's not, okay? And so the difference is, remember back when we went ahead and calculated the mean, median, the range, okay? So the range of values, okay, and among your x's is what you're going to use to determine whether or not it's a good idea to use this equation to predict something, okay? So in this case scenario, our range was 125, because that's the highest number, minus 70, okay? This was our range. This was our max, this was our minimum, right? So we used this, basically this equation is going to work as long as your x value, your future diastolic blood pressure readings for any patient, as long as those readings fall within this range, then this is a good equation to use for prediction. Okay, so when it falls in within this range from 70 to 125, okay, it's called interpolation, and it would be good to use. As long as your value is within that range, you should be able to get a pretty predictable h hat, okay? And that might come somewhat close to wherever however many appointments that person is probably going to require in the future. Now, if your diastolic blood pressure reading with your next, with the next patient that you're trying to see if you can predict, so if their diastolic blood pressure reading does not fall within this range, then you're in trouble. It's not going to be, this equation may or may not work out. Okay, so if it's like, if you had like a 69, well, it might, because it's very close to this at least. But the further it is outside of your range of values, the more it's not going to be a good idea to use this equation, because since it doesn't fall within these certain values, it's not very predictable. Okay, this equation was based on these readings. Okay, we did all that math with these readings. So this equation can only really predict with some accuracy readings that you would get with that only fall within that range. Okay, so if you ever get a reading that falls outside of that range, this equation would not really help you. Okay, and so any kind of value that falls outside of that range is going to be called extrapolation. Okay. Okay, so here's another look at interpolation. Okay, remember this is when the reading that you have or that you're given is going to fall within the range. Okay, the specific range that works with this equation. Okay, so it falls within that. So let's say your next reading, or let's say you do the same study in in another month, or maybe even 6 months from now. Okay, so you're trying to see how well this equation works with your new batch of patients. So the next patient in your study has a diastolic blood pressure of 80. And that is definitely within your range of X's. Remember, the range that we have for this data was 70 to 125. So 80 falls within that. Okay, so now we need to predict how many appointments this patient is going to have next year. So here's our equation. Remember our H-hat equation? So basically, we're just going to plug in the new X, which is 80, okay, into the equation to figure out an H-hat, which is going to be our prediction. Okay, so we went ahead and plugged the 80 into the equation. So over here, we get 1.1 times 80 minus 80. And when we do that, we get 8. Okay, so we're going to predict that this patient will come into the clinic 8 appointments next year. Okay, that's how easy, nice, and clean this equation works for only those values that are where it's like an interpolation. Okay, only for those values that fall within this range. It happens nice like that. Okay, so is it really that easy to make predictions using least squares line? Well, I mean, when it does fall within that range, then yes, but then again, here's another issue. What if you have a scatter plot that looks like this to your right? Isn't that crazy? I mean, does it really look like there's a line here or any kind of linear correlation? I mean, if we went ahead and of course, if we, if we use this data and we calculated for a line, we would definitely get a line. It might be like this or something. And yeah, there's some correlation somewhere. There's a little bit, but it's very weak, So would you think that this line is even a good line to use for prediction? It probably wouldn't work that well. Okay, so for, to evaluate if our least squares line equation should even be used for interpretation, because this might not give us very good interpretation of what's going on with our data. Our data is not very clean. We have too many scatters all over the place. So in order for us to determine whether or not we can actually get like a good line to work with and make predictions with, what we need to do is use the coefficient of determination. Okay, so finally we get here. This is going to tell us whether or not we even need to worry about predicting using this data for prediction, or if we should just chuck it or leave it alone or whatever we want to do with it. So let's dive right in. This is actually the coefficient of determination, or CD, and it's actually very, very helpful and super easy to calculate. Okay, remember from our last lesson we calculated R, right? Well, in this one we're going to do R squared. Okay, all this is R squared, and then we turn it into a percent. So just square your R and turn it into a percent, and then boom, we got the CV, or CD, I'm sorry. Okay, so for example, our R that we calculated in this problem that we've been working on for the last 2 lessons. Okay, so if you really need to go, you should go back to the last lesson and rewind it a little bit to see what our R was. But it was 95. So we calculated this last time, we got our 95. So what we have to do next is we're going to square the R. So that's 0.95 times 0.95, right? And that's going to give us 90, okay? And then we just turn this straight into a percent, which obviously, how do you turn things into percents? You move the decimal over 2 times, or times it by 100. So we have 90%. That's our CD. Okay, our coefficient of determination. Now, what does this even mean? So basically, this means that 90% of the variation that's happening in this data set, okay, happening in this data on the scatter plot, 90% of the data, okay, can be explained by our x, okay, or the 90% of the variation that's happening in our experiment or study is happening because of the diastolic blood pressure. Okay, so just to sort of like let you know, since the diastolic blood pressure was what we were following, that was our x. Now we're trying to see if the y follows the x, right? If it follows that variable. So since the y was the varied one, the one that we were thinking that the x should be controlling. Okay, this is really going to tell us how much of the y is the x controlling, in other words. Okay, so in this equation, the CD is what tells us that. So 90% of that variation happening in your y, the amount of appointments that the patients require, is happening because of the x, which is our diastolic blood pressure readings. So just given that, and just knowing that, that really tells us that the diastolic blood pressure does have that strong positive correlation with the number of appointments that patients have, which means that we can use it to predict how many appointments, or how many appointments that our patients are going to require in the next year, just by using this equation. Okay, just by measuring their diastolic blood pressure. That's pretty fascinating. But anyway, so what do you do with the remainder of that percentage? Okay, so what we're going to do next, after we figure out our CD, we already know 90%, we know that much, right? Well, what's with the remainder of the variation? Okay, so what we're going to do is take 100%, we're going to minus 90% because we got 90% here, all right, and then we get 10%. 10% of the variation that's happening in this study is unexplained. So 10% of the variation that's happening is not due to the diastolic blood pressure readings, but 90% of it is due to the diastolic blood pressure readings. Okay, so how we would write this in statistics, okay, like if you guys were writing a paper and you needed to explain this in your results, this is the language you would have to use. Okay, so you would say 90% of the variation in the number of appointments is explained by diastolic blood pressure, or DBP. And then you would say 10% of the variation in the number of appointments is not explained by DBP, or diastolic blood pressure. Okay, so that's really all it is. So what does that mean? Well, obviously, the higher the better. Okay, the higher percentage, the better, because that means that that the X is accounting for most of for that higher percentage of the variation. That means you figured something out, and then if it's super low, that means there must be something else happening here that you're not seeing. Okay, something else, there's a totally other variable in this situation that is causing the outcome that we're seeing. Okay, so it's not your X, or what you thought was your X. Okay, So really that's all that is. If it's a super low CD, a super low percentage, that means that a very small portion of the variation that you have in this data is accounting for the variation or the fluctuations in Y. If Y is going up or Y is going down. If you have a low percentage, then that means your X is not the one that is actually controlling that, and you cannot use your Y hat equation to predict anything, okay? Because it's just not going to happen. But if it is a really high percentage, then yes, you can use your Y hat equation to make predictions, okay? So in this lecture, I know it was a lot. I know that you guys are smart enough to handle this. So we went over quantitative XY pairs. We made a scatter plot, that looked like that to look at the linear relationship between X and Y, and then we looked at outliers. We calculated R to see if our correlation was positive, negative, weak, moderate, strong, and we did all this. Don't get confused. This we did in the last one, the last lesson, okay? Then today we went over how to figure out B and A and find our H hat, okay? Then we figured out how to understand residuals, what that means, and then also how to calculate our CD and to find out whether or not we can use our H hat equation as a predictor.